In this week's video, we will be discussing the intermolecular forces. We will be doing 3 problems this week. The first problem is, identify the intermolecular forces for each of the following substances. We have 4 very different substances, and we must look at the 3 intermolecular forces. The 3 intermolecular forces are London dispersion force, our dipole-dipole, and our hydrogen bonding. So for our first species, which is C6H12, we must remember that the CH only compounds are always nonpolar. This means that they will not have a dipole moment, and they cannot have a dipole-dipole for their intermolecular forces. Also, because it does not have oxygen, nitrogen, or fluorine, it can only have our London dispersion forces. This is the only intermolecular force between neighboring molecules. Let's look at our second example. Our second one is C2H5OH. We should draw the Lewis structure of this species, which I am doing currently, because it will help us not only with our dipole moment, but possible hydrogen bonding. Notice that our OH group is a hydrogen bonder. So this is one of our intermolecular forces. It does hydrogen bond, and it can be a donor with the hydrogen as well as an acceptor because of the lone pairs on the oxygen. So therefore, it can be a hydrogen bond donor or acceptor. It is also polar because of that carbon-oxygen bond as well as the lone pairs. Finally, because it has electrons, it does have London dispersion force. Our species, ethanol, has all 3 intermolecular forces. Our third example, H2SE, has a molecular geometry similar to that of water. It is drawn here with 2 lone pairs of electrons on the central atom. Because it does have electrons, it does still have London dispersion force, but because of that central lone pair set, it is going to be polar. This will give us a dipole-dipole intermolecular force. H2SE, we have 2 of the 3 intermolecular forces. Our final example for this problem is carbon dioxide. Drawing out our Lewis structure for carbon dioxide, you'll see that I have 2 carbon-oxygen double bonds. These bonds are polar, but because they are pulling opposite and equal from each other, we cannot have a dipole moment. It has only the London dispersion force. This is seen here. Also, because there are no hydrogens, it cannot be a hydrogen bonder. Therefore, our only intermolecular force is the London dispersion force. Identifying our intermolecular forces is the first of many problems that we will be doing today. Our second problem for today, select the substance that has the greater boiling point. So in this case, we are going to want to look for the strongest intermolecular forces. We have 3 pairs of compounds. So for our first compound, we have ammonia and pH3. What we will do is draw the Lewis structure for both species. There is the Lewis structure for ammonia. Notice the lone pair on the central nitrogen. Here is the Lewis structure of our pH3. Notice that they have both London dispersion forces because of each one having a pair of electrons. They are also polar because of that central pair of electrons. But let's look at this nitrogen. This can be a hydrogen bonder. A hydrogen bonding species means that it's going to have stronger intermolecular forces. So because this has all 3 intermolecular forces, our ammonia is going to be the greater boiling point species. For our second pair, let's look at CH3I versus CHI3. First thing that I'm going to do is draw the Lewis structure for both species. In the case of CH3I, it's going to be a tetrahedral species around our carbon. For our CHI3, it will also be tetrahedral by molecular geometry. We know that it will have London dispersion force because they both have electrons. But our CHI3 is going to have greater London dispersion force because of how big it is, with having the larger iodine atoms. Now you will notice that I'm drawing an arrow towards the iodines because these bonds are polar. For the CHI3, we are going to have 3 arrows pulling in different directions, giving us a greater dipole moment. So in this case, our CHI3 is going to be the greater boiling point species because it has a stronger London dispersion and the dipole-dipole. Now for example C, we have C2H6 versus C4H10. Just like we had in the first example, our carbon and hydrogen only species must be nonpolar. That means it cannot hydrogen bond or have a dipole. This means that it has London dispersion forces only. So now how do we break the tie? C4H10 is going to be larger. It has more electrons, it has a greater polarizability. Therefore, we are going to have greater London dispersion forces with the larger molecule. In this case, we now get C4H10 as having a greater boiling point. Our final problem for today, which solvent would you pick for the following solutes? We can choose water or C6H14, which is hexane. So now we need to look at the intermolecular forces of our solute and our solvent. Our first example is CaCl2. This is an ionic compound. This is going to dissociate into its constituent Ca2+ cation and 2 Cl- anions. Because these have charges, they are going to prefer polar compounds because of the permanent dipole and electrons in those various species. So how do we determine which one this is going to pick? We need to look at the intermolecular forces of our 2 solvents. Water, we know, has London dispersion force because it has electrons. It is also polar, so it will have a dipole-dipole. And finally, it hydrogen bonds. For our hexane, we know because it contains carbon and hydrogen only, it can only have London dispersion force. So because it prefers polar compounds, our CaCl2 is going to prefer the water. Our ionic compounds are more soluble in an aqueous environment. For our second compound, we have methanol, that is CH3OH. It is best to draw the Lewis structure. And now you can see here that I have an alcohol group with a lone pair. This has London dispersion force because of having electrons. It is polar because of the carbon-oxygen bond. And finally, because of the pair of electrons around the oxygen as well as having the hydrogen, this can hydrogen bond. Seeing that it has all 3 intermolecular forces that match up with water, methanol would prefer to be in a water environment. Just because it has carbon and hydrogen does not mean that it goes with the other carbon-hydrogen species. Our last species is carbon tetrachloride. This is carbon surrounded by 4 chlorines, creating a tetrahedron. But the interesting part about this species is that it does not have a dipole because all of our chlorines cancel out. So with having this, we know that it is going to be a nonpolar species. This means that it has the London dispersion force. While it does not have a dipole-dipole, and seeing there is no hydrogen or oxygen, nitrogen, or fluorine with lone pairs, we know that it can't hydrogen bond. This means that it will choose the C6H14 as its solvent. In these type of problems, you want to make sure that you go to the intermolecular forces of not only your solvent, but your solute. Choosing the correct intermolecular forces gives you the correct mixture and builds you the best environment. Good luck.